Propositional logic, part 4, truth tables for propositions. So if we have a compound proposition, like for example, tilde, parentheses, p dot q, close parentheses, wedge r, and if we want to do a truth table for that compound proposition, we have to figure out how many rows and columns our truth table should have. So the number of columns is going to be based on the number of simple propositions in our compound proposition. In this case, we have three simple propositions, P, Q, and R. Each of those three simple propositions is going to need its own column. And then in the fourth column, we can put the compound proposition. When you're doing this, it's convenient to write these simple propositions, P, Q, and R, in this particular case, in the order in which they occur in your compound proposition. In this case, the order in which they occur is the same as the alphabetical order, but in other cases, those could be different. In a sense, it doesn't really matter which rule or which custom you adopt for the order in which you write the simple propositions. But if you're taking a logic class and you need to compare your answers to those of the instructor or other students, it's convenient if everyone has the table constructed the same way. So for the purposes of this class, we'll be assuming that the simple propositions are written on the table in the same order in which they occur in the compound proposition. You can see here P occurs before Q in the compound proposition, and both of them occur before R. And then after you've figured out the number of columns of your table, you have to figure out the number of lines or rows. So this is based on the number of simple propositions you have. And there's actually a formula you can use to calculate this. It's L, the number of lines or rows, equals 2 to the nth power, where n is the number of simple propositions that you have. So the basic reason for this is that each time you add another simple proposition, you have to double the number of rows. So if there's only one simple proposition like P, there's only 2 rows in the truth table because there's only 2 possible truth values of P, true or false. But when you add another simple proposition like Q, that actually doubles the number of rows that you need from 2 to 4, because it's possible for both P and Q to be true. It's possible for P to be true and Q to be false. It's possible for P to be false and Q to be true. And it's possible for both of them to be false. And for the same reason, whenever you add another simple proposition, like in this case we have 3R, we have to double the number of rows in the truth table again from 4 to 8. Likewise, if we had 4 simple propositions, our truth table would need 16 rows. So the convenient way of calculating this is just by plugging in to our equation the number of simple propositions for n, and then we can calculate the number of lines or rows in our truth table. After we figured out how many rows it should have, we have to assign truth values to our simple propositions. And the way we do this is we have to follow a rule to make sure that each row has one of the distinct possible assignments of truth values to the 3 simple propositions. We don't want any rows to repeat. They all have to be different, and they have to cover all of the possible assignments of truth values. So the first rule is to start with the leftmost column, in this case under P, and the first half of the lines are given the truth value T, or true, and the second half of the lines are given the truth value F, or false. And then the second rule is to go to the next column to the right and basically divide the number of T's by 2 before flipping to F. So in this case, we had 4 T's on the leftmost column. When we move to the column to the right under Q, that means we're going to have 4 divided by 2 equals 2 T's before we switch to F, and then we keep switching until we finish that column of the table. We repeat this process of each time we go to the right, we divide by 2 the number of times T, or true, repeats before switching to F, or false. And then our rightmost column should alternate T and F all the way down, which is what we see here. And you can follow these rules to complete the assignment of truth values in the truth table, even if you have 4 or more simple propositions. So for example, if you had 4 simple propositions, P, Q, R, and S, then under the P, the leftmost column, there would be 8 T's followed by 8 F's. under the Q in the next column to the right, there would be 4 T's followed by 4 F's before they repeated, etc. Then, after we've created our truth table, we have to figure out the order of operations in our compound proposition before we can start assigning truth values. The basic principle is we have to start by computing the truth value of the logical operator with the smallest scope. If there's only one logical operator, then we do that one first. But if there's more than one operator, as you can see here in this particular example, we have 2 tildes and 1 dot. We have to figure out which operator to start with. And the general rule, like I said, is we start with the operator that has the smallest scope. So these 3 rules, if you follow them, you'll be able to assign truth values to the operators in the order of their scope from smallest to biggest. Rule 1 says, start with the operator in the most layers of parentheses. So in this case, we have one set of parentheses, and there's both a tilde and a dot in that set. So rule 1 helps us figure out it's either going to be the tilde or the dot in the parentheses, but there's 2 possibilities, so we have to look further to figure out which one to start with. Let's look at rule 2. If a negated statement is part of a compound statement, do the negation before the logical operator linking the compound. So, and that's exactly what we see in this case. We have a compound statement linked by the operator of dot or and one of those conjuncts in the compound statement, the first one, tilde p, has the not or the tilde before it. So we have to do the negation p, the tilde p, before we can do the dot. The third rule can also be helpful. If a compound statement as a whole is negated, do the logical operator linking the compound before the negation. This rule also comes up in this particular example because outside the parentheses is another negation. Basically, before we can compute the truth value of the negation outside the parentheses, we have to compute the truth value of the main operator in the parentheses, which is the dot. Before we can compute the truth value of the dot inside the parentheses, we have to figure out the truth value of the tilde because that negates one of the conjuncts of that dot or conjunction. So before we can begin, we basically have to look at the tilde operator and figure out how it's going to affect the proposition that it negates. In this case, we have tilde p. So do you remember the rule for the tilde operator? Like if you look at row 1, p is going to be true on that row. As you can see from the leftmost column, what is tilde p going to be? The answer is, for the first row, tilde p is going to be false. So the tilde always reverses the truth value of the operator. It always reverses the truth value of the proposition that it negates. So whenever, in this case, it's tilde p, so the tilde is negating p. Wherever p is true, tilde p is going to be false. Wherever p is false, tilde p is going to be true. The first 2 rows, p is true, so tilde p is false. Rows 3 and 4, p is false, so tilde p is going to be true. Now we have to figure out what is the next operator we should calculate here. Is it the tilde before or outside the parentheses, or is it the dot inside? You may remember from our previous discussion, it's going to be the dot inside the parentheses. And now you have to remember the rule for dot or conjunction. When is the conjunction going to be true and when is it going to be false? The answer is the dot or the conjunction is going to be false on any row where at least one of its conjuncts is false. It's only going to be true on a row where both of the conjuncts are true. You can see on rows 1 and 2, tilde p is false, so that means that the dot is going to have to be false. On row 3, though, tilde p is true, so we have to check the truth value of q, the other conjunct on that row. On row 3, q is given a truth value of t, or true. That means that the whole conjunction, tilde p dot q, that whole thing is going to be true. Now on row 4, tilde p, the first conjunct, is true, but q is false on that row, so that makes the dot false. And then we have one more operator to calculate. It's the tilde outside of the parentheses. So we know that the tilde is going to negate, it's going to reverse the truth value of the proposition that it negates. But what is the tilde negating? Is it negating the truth value under the tilde, or is it negating the truth value under the dot? The answer is it's negating the truth value under the dot. Because the tilde is outside of the parentheses, it negates the compound proposition inside the parentheses as a whole. The truth value of the proposition as a whole is going to be the main operator inside the parentheses, which is the dot. The dot has both conjuncts under its scope. It includes the tilde p and the q. It brings those together. The tilde in front of the tilde p is only negating the p. It has the smallest scope. So when we calculate the truth value of a tilde outside of the parentheses, we're negating or reversing the truth value under the dot. You can see on each row, the truth value of the tilde outside the parentheses is the opposite of the truth value underneath the dot. And in bold, the truth values underneath the tilde outside the parentheses are going to be our final answer for this truth table. You can put in bold or circle, if you're doing this by hand, the truth value under the main operator of the proposition. And it should be the last one that you calculate when you're filling in your truth table. So here's another sample compound proposition for us to figure out how to do the truth table of. So this compound proposition, tilde p horseshoe q, has two simple propositions, p and q. So it's going to have three columns in the table, one for each of the simple propositions and one for the compound proposition. And it's going to have 4 rows because we have two simple propositions. Remember, each time we add a simple proposition, we have to double the number of rows. One simple proposition like P only needs 2 rows. 2 simple propositions like P and Q need 4 rows. If we had 3 simple propositions, there'd be 8 rows, etc. Before we can calculate the truth values under our compound proposition, we have to assign the truth values to P and Q onto each row. So let's start with the leftmost column under P. Under P, we have to have 2 T's followed by 2 F's. Then under Q, we can alternate T and F. The rule is we start with half the rows under the leftmost column true before switching to false. And then when we move one column over to the right, if it's another simple proposition, we divide the previous number of T's by 2 to figure out the number of T's we have to write before switching to F. In this case, there's only 2 simple propositions. So under the leftmost column, we had 2 T's. That means when we move to the Q on the right, we're only going to have 1 T before we switch to F. Now we're ready to calculate the truth value of the compound proposition. So we have 2 logical operators, the tilde or the horseshoe. Which one do we have to calculate first? The answer is the tilde. It's because the tilde only negates the P. It has only the P within its scope, whereas the horseshoe has the entire compound proposition in its scope. The horseshoe links tilde P as an antecedent with Q as a consequent. So we start out with the operator has the smallest scope and then build up to the operator that has the largest scope. So when we are calculating the truth value of tilde P, how do we know what to write under the tilde? How do we do that? The answer is we begin by looking at the truth values of P on the left. The tilde is only negating the P alone. And then we have to ask ourselves, given that P is true on the first row, what would that make tilde P, etc.? So the answer is the tilde always reverses the truth value of the proposition that it negates. On rows 1 and 2, P is true, so tilde P is false. On rows 3 and 4, P is false, so tilde P is true. The next step is to calculate the truth value under the main operator, the horseshoe. So in order to do this, we have to look at the truth value of the antecedent and the truth value of the consequent. The antecedent is tilde P, so we look at the truth value under the tilde. The consequent is just Q. So we have to look at the truth value of the antecedent, tilde P, and the truth value of Q on that row to figure out the truth value of the horseshoe. So you can see the horseshoe is only going to be false in the case where you have a true antecedent and a false consequent. That only happens on line 4 of this table. On line 4, tilde p, the antecedent, is true, but q is false. So that makes our horseshoe false. On every other row, it's going to be true because either we have a false antecedent, or on row 3, we have a true antecedent and a true antecedent and a true consequent. So that makes the horseshoe true. Let's look at another simple proposition, tilde p triple bar q. Like the previous example, this has only two simple propositions, p and q. So our table is going to have 4 rows or lines and 3 columns. So to begin with, we assign the truth values under p and q. The next step is to figure out which of the operators we should look at first, the tilde or the triple bar. Which one of those do we have to calculate first? We start with whichever one has the smaller scope. So that's going to be the tilde in this case. The tilde only negates the p, whereas the triple bar links together both the tilde p and the q. So the rule for the tilde is it reverses the truth value of whatever proposition it negates. In this case, on rows 1 and 2, p is true, so tilde p is going to be false. On rows 3 and 4, p is false, so tilde p will be true. Now we can calculate the truth value under the triple bar. In order to do so, we have to look at the truth value of tilde p on that row and of q on that row. So the rule for the triple bar is that wherever its 2 propositions that it links have the same truth value, the triple bar is true. Where the 2 propositions it links have a different truth value, the triple bar is false. So we can see on rows 1 and 4, tilde p and q have different truth values. That makes the triple bar false. However, on rows 2 and 3, q and tilde p have the same truth values. That makes the triple bar true. Now let's do another sample problem. In this case, the compound proposition is p dot tilde parentheses r dot s close parentheses. Now, in this case, we have 3 simple propositions, p, r, and s. That means our truth table is going to have 8 rows. It also means that our truth table is going to have 4 columns, 1 for each of the simple propositions and 1 for the compound proposition. Let's begin by assigning truth values underneath our simple propositions. We start with the leftmost column and we alternate half of the rows t and then the remaining half of the rows f. Then when we move to the next column to the right, we divide by 2 the number of t's before we switch to f. So under the r we have 2 t's then 2 f's, 2 t's then 2 f's until we finish the table. Then when we skip to s, we divide by 2 again the number of t's we had before we alternate to f. So this is what all of your truth tables with 3 simple propositions should look like as far as the assignment of truth values underneath the simple propositions. Now we're ready to calculate the truth values of the compound proposition itself, but we have 3 different logical operators to calculate. We have a dot outside the parenthesis, a tilde outside the parenthesis, and a dot inside the parenthesis. So which one of these do we start with? The rule is we have to start with the one with the smallest scope. So in this case, it's the dot inside the parenthesis. The dot only covers the r and the s inside the parenthesis. It does not have in its scope anything outside. Now we have to remember what the rule for the dot is. In order to calculate the truth value of the dot inside the parentheses, we have to remember the truth values of its 2 conjuncts, r and s. So we check the truth values of r and s on that row, and then we use those to calculate the truth value of the dot. The rule for the dot is it's only true where both of its conjuncts are true. You can see on row 1, both r and s are true, and so that makes the dot true. Also on row 5, r and s are true. That makes the dot true. On every other row though, rows 2, 3, 4, 6, 7, and 8, at least one of those conjuncts is false, and that's why the dot is false on that row. So then we have to figure out what is the next operator to calculate, the tilde or the dot outside the parentheses. Well, we have to figure out which of those has the smaller scope. In this case, it's the tilde because it negates only one of the conjuncts of that second dot. The tilde is negating r dot s. It's not negating the rest of the proposition. So it has the smaller scope. It's the second conjunct that's linked to by the dot outside the parentheses. So then we have to figure out how to calculate the truth value of the tilde on each of those rows. The answer is that we negate the truth value of the proposition inside the parentheses. The proposition inside the parentheses, the main operator is the dot. So that's the truth value we're negating with the tilde. So when the dot is true on a row, like rows 1 and 5, the tilde is going to be false and vice versa. So then we only have one more operator to calculate, the dot outside of the parentheses. And we have to figure out how do we calculate the truth value of that dot. We have a bunch of different truth values on our table for each row. Which of the ones are we looking at to calculate the truth value of that dot? The answer is we have to look at the truth value of P on that row because that's one of the conjuncts. And the other conjunct is not parentheses r dot s close parentheses. So we have to look at the truth value under the main operator of the second conjunct, which is the tilde. So the tilde is the main operator of the second conjunct. So on each row, we'll compare the truth value of P and the truth value under the tilde to calculate the truth value of that dot outside the parentheses. So you can see the rule for the dot is it's only true when both of the conjuncts are true. That happens on rows 2, 3, and 4. On rows 2, 3, and 4, both P is true and the tilde is true. So that makes the dot outside the parentheses true. On every other row, though, at least one of those is false, and that's what makes the dot outside the parentheses false. Like, for example, on row 1, P is true on that row, but the tilde is false, so that makes the whole conjunction false.